Control Systems, Lecture 3, Electrical Network Transfer Functions, Part 1. By the end of this lecture, students should be able to model electric circuits using transfer functions, analyze passive networks, including RC, RL, and RLC circuits, apply transfer functions to operational amplifier circuits, and use MATLAB to simulate circuit responses. So in this particular section of the textbook, the author applies the transfer function to solve electric circuits, and he has this table 2.3, that shows the relationship for each component that we're going to deal with: capacitors, resistors, inductors. He shows the voltage current relationships, the current voltage relationships, the voltage charge relationships, and the impedance relationship for each circuit. He also shows the admittance. We're going to make use of the impedance circuit to try to simplify our analysis. So for the capacitor, we have the following relationship. For the resistor, inductor, we're going to define the following transfer function, Z, to be the voltage divided by the current. And you can see each one of these is sort of written in that sort of form, right? For example, we could solve this one as Z would be equal to the V over R. This one, Z would be equal to V over Ls. And for the capacitor, Z would be equal to V over times CS. So let's say we have a typical RLC circuit. Back in your physics class or your electric circuits class, you learned to solve this by using Kirchhoff's loop rule or using a mesh equation, depending on what class you took, and then developing a differential equation and then solving that differential equation to figure out what the voltage of the current did as a function of time. Well, since we're trying to deal with transfer functions, we want to take this whole circuit and transform it to what's called a Laplace transform network. So let's take it step by step. So first of all, we'll transfer the voltage into Vs. Here we have an inductor. So back in the previous table 2.3, there's a relationship that said the voltage equals Ls times Is. So here, the L becomes a Ls, because what we're going to transfer, we're going to look at the current flowing through here. So over here, the current was a function of time, but in our transform network, the current's a function of S. So the inductor the L gets replaced by an Ls. For the resistor, it's the same as it was. R gets replaced by R, based on this relationship. And for the capacitor, the C gets replaced by 1 over CS. This is our Laplace transform network that we're going to use to solve this circuit. So now we simply write a mesh equation using the impedances. So we start here, we have V sub S equals Ls times the current plus R times the current plus Is divided by CS. So each of those terms has an I in it, so we can factor the I outside, and we're left with the following constants inside the brackets. So if we solve this for the current divided by the voltage, we get the following relationship. Now we can replace, what we're really interested in is how the voltage relates to the voltage across the capacitor relates to the voltage of the source. So we can replace Is by its equivalent, CS times Vc. This goes back to the impedance term again. So we simply, when we see Is, we replace that by Vc times Cs. And then we can solve this. So continuing from our previous slide, we have the current divided by the voltage is given by this term here. So we can solve this, divide both sides of the equation by C times S to arrive with our output that we need that relates the voltage across the capacitor to the input voltage given here. So this is our transfer function. We'll define it as H of S, given by this relationship. So this is a very simple MATLAB script that you should run that sets up the transfer function that we just saw for. This creates the transfer function, and this plots a step response to the transfer function. So again, you should plot this out and verify that you understand how to use MATLAB to generate the transfer function and get a plot out.